Hello, everybody. So we have one person online so far and 2 people in class. My today's lecture is going to be devoted to cleaning up my previous lecture. At this point, you might say, well, that's because you're sloppy, you don't prepare well enough, and so on and so forth. Well, maybe you're partially right, but I would like to explain that this is the price you pay for lecturing on ongoing research. Simply, I mean, even if you have a Fields Medal, even if you're an absolute genius, it's almost never possible that you get everything right at the first go, all right? And this is what happens. So I'd like to today it's going to be a very brief lecture, testing equipment in room 106. You can see that we have fancy view from the camera. You should see the blackboard, you should see me, and you should see people in the room. So yeah, maybe. Yeah, I think you're visible. Yes, 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 okay. You're visible, and in fact, this microphone is so good that it records me, and if you speak, you will be perfectly, people will be able to hear you perfectly. Okay, so for starters, I would like to go into an example of an M condition. Remember, I had this M condition, which was saying that we have a path homomorphism of graphs, and if we take two edges, E1 and E2, and f of E1 is less than equal than f of E2, but it implies that E1 is equal to E2, all right? And if you look at these two graphs, E and F, okay, there is the only possible map, the constant map, there is no other map possible. Then you can see that this M condition fails, right? It's clear because this part is true because point is less than equal than a point, vertex is less than equal than a vertex, but E1 is not equal to E2, okay? However, as I realized, the constant map still induces an evaluation map from the conpath algebra of E to the conpath algebra of F. If you look at the conpath algebra of this graph, oops, I shouldn't write it. I think it's so thick. Okay. If you take the conpath algebra of this graph, because here the conpath algebra of this graph is just the ground truth, right? That's all. But this one is actually the universal algebra generated by two isometries. And that's okay. This is like the free product of two Tepes algebras, if you complete. And when you have a free product, you can divide it by the sort of commutator. You always can go from a free product to the tensor product. Now, from the tensor product of Tepes algebras, you can go to the classical torus. On the classical torus, you have the evaluation map. So by all means, this map exists, okay? And it's in fact induced by the constant map here. So what I realized is that the M condition is still not optimal, okay? I believe, but I didn't have time to check everything and write everything. I believe that if we have a situation in which we have a map from a path homomorphism of graphs from E to F, which satisfies the M condition, so that, you know, we have this covariant factorial lemma about the conpath algebra. I think that if we do the following trick, that at any vertex of a graph E, we add an arbitrary number of loops. It can be infinite, it can be uncountable, you name it. That's not important, right? And then you extend the path homomorphism of graphs by collapsing all these loops to the base point, okay? Then I believe it will still induce path a homomorphism between conpath algebras. But I didn't have time to check it, and I didn't have time to rewrite it. So I'm giving you this example, which clearly fails the M condition. But on the other hand, it still induces a path homomorphism between conpath algebras. But that's something very difficult to specify. I don't quite know how to weaken the M condition so that it accommodates this example. What comes to my mind that maybe instead of E1 equals to E2, I should say that S of E1 equals to S of E2 and T of E1 equals to T of E2. Maybe that works, but I don't know. You see, that's an open research problem. Okay, now let's go on. Now I want to dwell a little bit on this regularity condition. And this construction, as baroque as it seems, it actually cannot be simplified. So in fact, a week ago, I gave you a wrong argument in the proof of the lemma, and I'm going to rectify it. But before I do it, I want to give you some examples and counterexamples for the regularity condition, because that's what we didn't do yet. So first, if you look at number one, it's completely clear that this is the simplest case when what you are doing when you construct your FP-FV in the following way, that you take all edges that start at FV and you set them all aside. So the only paths that you have are paths of length 1. And then if you have a bijection between these sets of edges, of course, number 2 is satisfied. Okay, so that's like the easiest case, and this is exactly what you would find in textbooks. Because in textbooks, people typically don't go into path homomorphisms of algebras, which is a big drawback, and I'm going to explain it in a week, why we need it. All right, so that's like the canonical example of a path homomorphism of graphs which satisfies this regularity property. Okay, now another example is as follows. You take again just one loop and one vertex, so you have again the constant map, and obviously this is not regular, okay? Because here I have one edge emitted from a regular vertex V, and then I map a regular vertex V to a sink, which is not a regular vertex. So it already goes wrong, right? But you can see that here I have one edge, and here I have zero paths, okay? So that's definitely not regular. However, despite this, this induces a homomorphism of Levitt-Pav algebras, because that's just an evaluation. If you look at the Levitt-Pav algebra of this graph, this is nothing but Laurent polynomials. And you take your generator and you evaluate it at 1, and you get a number. It works beautifully. That's exactly what you are doing. You are sending this E to V, so you're evaluating the generator at 1. That's all. Yeah? So it works, okay? So again, therefore, we might relax the regularity condition. And here, that's a little bit more subtle, because we are talking about the Kunz trigger relation type 2. So it is sensitive to what is emitted from your vertex. When we are talking about the Kunz trigger relation type 1, I could say, okay, I take any vertex and I attach as many loops as I want. And then I have just a map collapses these loops. That's okay, because here we have some projection V. This projection V is mapped into the projection V. And of course, if you have some any loop here, then the first Couplé relation just says that E star E is equal to V. So if I substitute V for E, then I have V star V is equal to V, which is of course true, because V is a projection. So V star is V and V squared is V. So that works, no matter how many loops you take. But now when you're looking at the other configure relation, well, you wouldn't be able to do it with more loops. Because you can, it's no longer true that E star is equal to V. You'd have to have EI star and sum over I. Okay, so that's getting more complicated. And basically, in order to do this kind of collapsing magic, you must not have anything else emitted from your vertex but your loop. So this means that what you have a hope of doing to somehow generalize this simple example or counterexample is that you attach single length 1 loops at sinks. Yeah. If you have a graph, oops, I should write not with an eraser. If you have, say, a graph with sinks, say like this, and then you have a morphism which satisfies a regularity condition, okay? Then I can, this is map G, okay? Then I can always attach one single length 1 loop at any sink. So I can attach it here, I must not attach it there, all right? And then I enlarge the map F by saying, okay, these loops are just collapsed to the base points. So this loop is mapped to this vertex, and this loop is mapped to this vertex. And again, this Kunz-Krieger relation will be satisfied because here what you have is this is V and this is W. So sorry, maybe I should write it like this. Okay. And this is again V and this is W. When you have a relation E star equals to V, that's because it was a single, to V, sorry, not to E. And then again, if you replace E by V, you have V star equals to V. This is true in the other graph. So you don't violate it. And then you see how this extension of M condition with extension of a regularity condition coincide. Before I told you that I believe that we can have assumptions by saying that it's permissible to attach arbitrary number of loops of length 1 at any vertex. And here I'm telling you, well, you can attach only one length 1 loop at only the sink. That's a special case of the previous case. So this should really rock and roll, and then both M condition and the regularity condition should be satisfied. Okay, so this is the way we should be able to make our covariant punctuality theorem more general. Okay, but again, I didn't have time to check it and rewrite it, and I think it's more important for me to prove for you the push-out to pullback theorem in the contravariant setting than to go more into this covariant setting. But that's this is important for Mieszko because he will talk about this stuff on Friday. So these are the corrections I had in mind. Okay, and this is the correction I didn't get to that. But I explained how we can weaken this regularity condition. But again, it's not so easy to write it down. I don't know how to write it down except the way I explained it to you. Maybe you should not change the regularity or M condition, but change assumptions of the lemma. Say that da be regular, and then we can attach collapse, stuff like this. That all requires time. Okay, let's do another example. Now, this is a typical example. I have my graph E, which is one edge, and I have my graph F, which are two edges and three vertices. And basically what you are doing, you are mapping V to A, W to C, and E to XY. And then, of course, this satisfies the regularity condition, okay? Why? Because you see, I extend I don't set aside my edge X, which is emitted from F of V, which is equal to A. I don't set it aside, but I extend it. But it's important, I extend it by all edges emitted from V, from the end of this edge. That's why it's okay. If I would draw here another edge, this would be wrong. This wouldn't work. So this is like the easiest example of this regularity condition, which is non-trivial, which generalizes what you can find in textbooks. Why? Okay, good. Now this time a counterexample. So now you see this lambda as my graph E. And here I have a Potlatch sphere graph as F. And you can see that there is no regular path homomorphism from E to F. Why? Because you see, you have only one regular vertex in this graph, V. Okay, that's the only regular vertex here. And that's the only regular vertex, V. So if you have a regular homomorphism, it must map V to V. Okay, that's why I labeled by the same letter. But now you have a problem because the amount of all edges that you have emitted from V is 2, whereas the minimal amount of all paths emitted at V in F is at least 3. We have more paths, but if you want to involve S is defined in the regularity condition. If you want to involve all edges, well, you have at least 3 paths. There's no way around it. So there's no regular path homomorphism, okay? And now it's something which is very dear to my heart because it goes back to my PhD thesis. You see, if you take the graph sister algebra of this graph, then this is in fact the real quantum projective plane. And if you take the sister algebra of this graph, well, I didn't define it formally, but you know what the Levitt-Pav algebra is. and take the ground field to be complex numbers, take that star to be an involution when you have a star algebra, and take the universal enveloping C-star algebra. Okay, that's the way you do it. This is the Teplitz algebra. So if you want, these are continuous functions on the quantum disk of Klimek-Leśniewski. Okay, and you see, this is a very deep geometrical meaning, because if you think about classically about real projective space, how do you define it? You take the sphere and you identify antipodal points on the sphere. But there is a little bit of redundancy there, right? Because if you have something in the upper hemisphere, there's a point in the lower hemisphere. So forget the upper hemisphere. Just take the unit disk corresponding to, say, the lower hemisphere. Well, you're almost done. But then you have the boundary circle, the equator. So then this antipodal identification will say, aha. So in fact, RP2 is nothing but the unit disk, but with the boundary points identified by the antipodal map. Okay. But then if you look at all continuous functions on the disk and all continuous functions on RP2, you can say continuous functions on RP2 are simply continuous functions on the unit disk, which are constant under the Z2 acting antipodally at the boundary, right? So this is why it is a C-star subalgebra. And indeed, this is also true in the non-commutative setting. This is injected in here, okay? So in fact, this example has some deep topological meaning, but it's also a very nice example which shows that indeed it satisfies a regularity condition. Well, we identity on vertices, V goes to V, W goes to W, and what happens with E0? E0 is mapped to U star, U squared, E1 is mapped to E, and E2 is mapped to UE. So you see that this is definitely a path homomorphism of graphs. And why does it satisfy the regularity condition? Well, that's because what I'm setting aside my edge E, that's set aside, that gives me path of length 1. And then when I take U, I extend it by both outgoing vertices from V. I extended it by U itself, and I extend U by E. That's why I satisfy the regularity condition. Okay. And then I have these 3 edges emitted from V mapped to 3 paths over there, and this does induce, this satisfies the regularity condition. We should also check the M condition and so on, and I'm not certain that this map will give me this exact inclusion of C-star algebras I'm talking about here. I didn't check it, but with a little bit of twiddling around, it might work. Anyway, I find it as a very beautiful and non-trivial example, and not motivated by non-commutative topology, which shows you that, look, this is a very nice way in which the regularity condition works, okay? And you wouldn't be able to do it in the naive way, because if you do it in the naive way, then V is a regular vertex emitting 3 edges, and on the right-hand side, in F, V is a regular vertex emitting 2 edges. So this naive regularity condition, as you find in textbooks, I mean this one, okay, it doesn't hold. But that's wrong. This really cuts down important topological examples. Okay, and let me give you one more counterexample. And I'm giving to you this counterexample because this is exactly what forces me to modify the argument in the proof of lemma 2.46, which I gave a week ago, which was not correct. Now it's correct. So you see the graph, okay, and we are mapping V to V. Well, I mean, we have 3 vertices here and we have 3 vertices there. So you know what goes where, right? And now we make the following assignment. We map E0 to X1, Y1. So that's okay because it starts at V and ends at U. That's okay. This is how it happens on this picture. Then E1, I map to X1, X2, X1, Y2. So I go from V to W, and that's okay because E1 goes from to W. And likewise, I map E2 to X2, Y2. So this is a legit path homomorphism of graphs. So what goes wrong? So you see, despite the fact that all these edges, X1, X2, Y1, and Y2, they are part of paths emitted from V, which are in the image of my edges, okay? So you can say all edges are involved, we are good to go. No, the problem here is that we are missing x2, x1. So what happens is that when I don't set aside my edge x2, I must extend it by all outgoing edges, both y1 and y2. And it doesn't matter that we only use y1 and y2, because we use y1 and y2 in conjunction with x1. We must use it in conjunction with everything, which is extended. So my argument before came to saying, okay, so all edges take part in paths, that's wrong. I mean, this is a counterexample. But it's very easy to rectify. It starts here at this part of the proof. That's the part which I want to rectify. So for starters, all vertices involved as emitters of edges contained in paths in this G, FP, FV are regular because all such emitters in FPV are regular and G maps regular vertices to regular. That's obvious, right? So here there's no problem because again, all these emitters in FPV are regular and G of regular is regular. So the first condition of the regularity, I mean, first condition, part of a condition, it's written here. You see, we require, where is it? Whose all edges begin at regular vertices, right? So this is that satisfied. Okay. Now we go on next. At each such an emitter W in FPFE, we replace the set of all edges emitted at this W by set FPGW. So indeed, it is true that all edges in E contained in paths in G, F, P, F, V are either terminal, they are no longer extended, they are set aside. I mean, the path in which they end a certain path and they are no longer extended, or extended by all edges starting at the end. That's because of the definition of what we have in F, P, E, V, and that we replace this array of edges by array of paths. But in the definition of the array of paths, we use all edges. All edges must be involved in these paths. So that's true at these vertices at which we jump, at these GW vertices, but at all these internal vertices at FPGW inside, you know, it's the same story by the very definition of what FPGW is. I mean, we always extend, we either terminate or we extend by all edges, okay? So it's exactly the same argument as before, but I cannot argue by this involvement of an edge in a path. No, it has to be that every path is either terminates at a given edge or is extended by all following edges. Okay, so I think that this proof is rectified. So Mieszko, this is for you, so that you have a correct picture for your talk. Okay, how are we doing in time? Okay, 23 minutes. Now, I think I want to go to the contravariant side. And I just want to show you two elementary facts. And this will be the end for them. Okay, elementary facts. This is what we are talking about. So remember when we are verifying this lemma 2.48 that we really have a subcategory with this target bijectivity condition. So remember, this is the target bijectivity condition, okay? When we restrict, when we look at this TE, for every X in F1, for every edge in F1, then this map must be bijective, okay? That's the target bijectivity condition. And we checked, that's obvious, that if the map F itself is bijective, then target bijectivity easily follows. So so it works for F equal to identity, which is necessary. But now you might be tempted to think, well, how about if F is just injected? What if F is injected? Okay, does it work then? And remember, this is the contravariant scenario. So these are graph homomorphisms. So we have just F0 and F1, we just map vertices to vertices and edges to edges. Okay, so the injectivity of F means injectivity of F0 and then injectivity of F1. Okay, so you might think that maybe injectivity is enough. No, wrong. So if you look at the injective graph homomorphism, an injective homomorphism of graphs, it need not satisfy the target bijectivity condition. Indeed, if you map the one vertex graph into the one loop graph, so what we are doing is very simple. This is our, oops, sorry. That's too thick. Okay, this is our V, and this is our loop at V. Okay, and we simply map V into V. All right. So obviously, this is an injective homomorphism of graphs. The set of edges is empty, and V is mapped to V. That's an injection as well. Okay. But why the target bijectivity fails? Well, that's because if you look exactly at this condition, sorry, no, if you look exactly at this target bijectivity condition over here, what happens is that this set on the right-hand side, the counter domain, is not empty. It has V, okay? But this one is empty because there is no preimage of a loop, it's empty, okay? So mapping an empty set to one element set is hardly ever a bijection, okay? So this is an example where this is not a bijection. And here, and for a while, it got me worried because remember, we are in the contravariant situation. So we are looking at I have to make slightly thinner pen. You see, if I go from now the Levitt path algebra of a loop to the Levitt path algebra of a point, which is just the ground field, okay, you can say, wait a second, such a map exists, just an evaluation map, right? So what's wrong? Well, the thing is that this map is not induced by this model. And you can just directly check it. But if you use this map induced by this injection, the map would map this generator E, the loop, it would map it to 0. So sorry, but if you have Laurent polynomials and you send the generator to 0, this will not give you a homomorphism of algebras. This map will not exist because you can U1 equals 1. So if you map U to 0, 0 times whatever is 0, not 1. So that does not work. Okay, so such a map exists, but it's not induced in a contravariant manner. Okay, so that's important. But now there is another fun fact which we will need in our push-out to pullback theorem, which is the following. Now let's reverse the situation a little bit partially. Now we take a graph homomorphism which is injected on vertices and satisfies the target bijectivity condition. Then it's also injected on edges, which means it is injected. So when we tried injectivity on edges and injectivity on vertices, it did not imply the target bijectivity. But if you take the injectivity on vertices and target bijectivity, then we have injectivity on edges as well. And this is a very simple argument, okay? So we take two edges, E1 and E2, such that f of E1 is equal to f of E2, okay? But then obviously, E1 and E2 are in the preimage of f of E1 by definition. So that's on the one hand side. But on the other hand, you see, of course, you have this set, which is the preimage of the end of f of E1 is non-empty because the end of E1 and the end of E2 are inside, so this is not an empty set, okay? But remember, we are injective on vertices. This is a vertex, okay? So preimage of a vertex is either an empty set or one element set, because it's not empty, it's one element set. So this means that this set is one element set. Well, because E1 and E2 are in one element set, it means E1 is equal to E2, okay? And this is a very, very important conclusion for us, which we are going to use in a week. And I think this is everything I wanted to say in this lecture. I cleaned things up. We are now ready to go for the final hit, which I hope will be the theorem of the semester. and this is push out to pull back theorem or Levitt-Pap algebras. If I will not manage to give you the full proof, at least I want to phrase the theorem and tell you the ingredients that I needed. But basically, there are incredibly many ingredients that I needed. I need my lectures about graphs from the first semester. I need my push out to pull back theorem for path algebras, which was the theorem of the previous semester. So I need two main theorems of two previous semesters. And then I need all the work thus far that we get about the contravariant functorial algebra Levitt-Pap algebras. I have to combine the three big giants together. But that's not everything, because I still need to verify that I really have a pullback at the end of the day. So I have these Pedersen conditions for my graph being the pullback graph, and then I need to see that certain ideals intersect to zero, but it's hard to compute. So what you do, you then do completion in the sister algebra, and for the sister algebras, intersection is equal to multiplication, and then you prove that the completed ideals multiply to zero, which means that the completed ideals intersect to zero, and because these non-completed ideals are inside them, they also intersect to zero. So, I mean, I have to involve lots of machinery, grading, a lot of structural theorems, and you can ask, why just for Levitt and not for Comp? The reason is that, you know, if I want to prove that push out to pull back theorem, I must have structural theorem about ideals. And when you look into a book, the Levitt-Pap algebras book, you have structural theorems for ideals inside Levitt-Pap algebras, not Kohn-Pap algebras. But we shouldn't despair about it, because remember, and at the end of the day, any, even relative Kohn-Pap algebra is always Levitt-Pap algebra of a modified curve. So I'm not actually losing much, okay? But the amount of things you have to use is enormous. I really have to put together three major theorems from my own lectures, and some major theorems, a number of major theorems from the book, and even go as far as to the sister completion in order to make my argument work. So that's quite a lot of work. So I'm not certain that even in over 2 hours I'll be able to present it, but at least I want to formulate the theorem and tell you what steps I needed to prove it. Okay, but for today it's everything. Thank you so much, guys. Let's see at 3 o'clock sharp in another room, and I stop recording and see you in half an hour.